mesodermal structures are formed and they're patterned along the anterior-posterior axis by the movement of Henson's node, as well as and they're derived from tissues in the primitive streak. Okay, so as I mentioned, Henson's node migrates. It's a region of cells that migrates from the anterior to the posterior end. And so similar to the mesodermal patterning that we saw in the Xenophus, where you have dorsal ventral patterning, right, of the mesoderm, the same kind of patterning occurs in the chick. So as the node moves, this is the anterior, imagine the anterior end of the chick, and this is the posterior end of the chick. Here's the node. And what these arrows depict are the tissues that will form, or the mesodermal tissues that will form after this node passes them. So, for example, the most anterior structures that are mesodermal are the notochord and the precordial pid. As Henson's node moves down, you'll start to get what are called medial somites. So these are the somites that are more close to the future spinal column. As it moves past, you start to get the production of lateral mesoderm that produces another part of the somite. As you move more posterior, you start to get mesoderm that will develop into kidney, and then another section of mesoderm called lateral plate mesoderm, etc. So the idea is that the patterning of the mesoderm from anterior to posterior results in mesodermal tissue. They'll all stain with brachyury, but they'll eventually develop into a different type of complex tissue. So in the mouse, patterning of the mesoderm also occurs similar to the chick. So in the mouse, there is still an area called the primitive streak. And as we talked about earlier, the primitive streak is located where the future posterior side of the embryo will be. And its location is induced by signals from the anterior visceral endoderm. Okay, so if we compare and contrast patterning of the mesoderm in the Xenophus and in the mouse, even though they look very different, there are some similarities. So, for example, in Xenophus, BMP4, nodal, and Wnt are expressed in what will become the future mesoderm. And in the mouse, nodal and Wnt are also co-expressed in the primitive streak, and they are required for mesoderm formation. Let's see. Also, nodal and Wnt signals in Xenophus are inhibited in the organizer region, here at the dorsal side. But in the mouse, nodal and Wnt signals are not inhibited in this primitive streak. In Xenophus, brachyury is expressed throughout the mesoderm, just like in the chick, also in the mouse. And this gene called boostoid is expressed only in the organizer. In the mouse, we see that BMP4 activates brachyury, so it activates mesodermal genes in the primitive streak, and that nodal and Wnt activate this gene boostoid in the node. And the node is another organizing region that we will discuss in a few more slides. Okay, so it's hard to see here, but this is the signaling pathway that occurs in different areas of the mouse embryo. Okay, so you can see here that BMP4 and BMP receptor 1 are involved in the activation of this transcription factor brachyury. There's some signaling feeding into the expression of boostoid in the node. So the take-home message of this slide is that as I've been telling you all semester, that signaling pathways in all of the embryos that we've discussed are conserved, and in mesoderm induction, they're very highly conserved. So there's a lot we can learn from jumping around from different model organisms, especially for vertebrate mesoderm induction. So in the mouse, the future, as I mentioned, the cells that will become the primitive streak are present, they're present in this kind of broad area. There's these little dots here in the early embryo. And then as the anterior visceral endoderm migrates and signals to where the primitive streak will be, these cells of the future mesoderm will migrate to that area. So there's a lot of active rearrangement of cells in the mouse embryo at this time. And you get a primitive streak that then expands. And basically what's happening in here is you're getting patterning of the mesoderm that is being produced by the primitive streak. So here's the primitive streak shown in purple. Below it is the node region, the organizing region. And then what you see is that these different types of mesoderm, for example, axial mesendoderm, it's a mixture, it's a tissue that kind of looks like mesoderm, kind of looks like endoderm. Okay, it's basically induced from the primitive streak. And so you start to get different patterning and tissues formed from the primitive streak, similar to what we see in the other embryos. Okay, so that's it for just how mesoderm is induced. And so next, we're going to pick up now how a specific type of mesodermal tissue called the somites are induced. So, our objectives now are to understand how mesoderm is fated to become these somites. And we'll talk about spatial and temporal control of development again when we talk about semitogenesis. You'll see how a somite knows whether it came from the anterior side or the posterior side. And we'll see examples of how circadian clocks, so biological clocks, actually control when individual somites are formed. I'm going to talk about a signaling pathway called Notch signaling, so another signaling pathway. It's very important for semitogenesis, and so I'll introduce that to you today. And we'll come back to the discussion of Hox genes. So you may recall Hox genes on Drosophila are the ones that are expressed collinearly. So they're expressed in the same order in the genome as they are in the body. And they're the genes that when you mutate them in the Drosophila, you get the antennas coming out of or legs coming out of where the antennas will be, or duplicating different sections of the body. In vertebrates, the Hox genes are also important for patterning the anterior to posterior axes, and for somites, they help identify if that somite is a more anterior somite or a posterior somite. And then I'll talk about different experiments that you can also use to understand how somites patterning and differentiation occur. Okay, so the development of somites is called somitogenesis. And this is a picture of what kind of embryo do you think it is? What is it? Chick? Good, okay. Yes, this is a chick embryo. Okay, very good. Okay, so this is the